sequences are just the list. 2, 4, 6, 8, 10. That's an arithmetic sequence. A series means you're adding them all together. Okay? And there's a new symbol you have to know. This is summation notation. This is the letter sigma in the Greek world. What this means is that says m equals 1. And then at the top it says 6. That means you plug in an m of 1 to your expression, and then you plug in an m of 2 to your expression, all the way up to 6, and you add them all together. So if I plug in a 1, I'm going to get 1 squared plus 1 over 1. That's going to give me 2. If I plug in a 2, that's 2 squared plus 1 all over 2. That's going to give me 5 halves. If I plug in a 3, 3 squared plus 1 over 3 gives me 10 thirds. Plug in a 4, 4 squared plus 1 over 4 gives me 17 fourths. And if I plug in a 5, gosh, I did this the long way. 5 squared plus 1 over 5 gives me 26 fifths. And then plug in a 6. 6 squared plus 1 over 6 gives me 37 sixths. And I'm adding all of these together to get a grand total. So on your calculator, 2 plus 5 halves, plus 10 thirds, plus 17 fourths, plus 26 fifths, plus 37 sixths. And you get 23.45. You can just trust me on that. So in number 2, I'm not going to do it, but I would plug in a 4, plug in a 5, plug in a 6, plug in a 7, add them all together. Follow? Number 3, I would plug in a 1, I would plug in a 2, I would plug in a 3, I would plug in a 4, add them all together. Number 4 is interesting. If I were plugging in a 5, what would I get? 3. If I were to plug in a 6, what would I get? 3. So you're going to do that technically, but you don't have anything to plug it in for because it's a constant function. So you're going to get 3 plus 3 plus 3 plus 3 plus 3 every single time until you get up to your 10th term. And then just add them all together. Okay? Yep. Yep. Is what? So it would be 3 times 4. Oh, you're right. It should say J. Sorry. Yeah, that letter that you use on the bottom should match the letter that you're plugging it in for. So that's just a typo. Good catch. Okay, so that's what sigma notation means. Oh gosh. I kind of jumped the gun on it a little bit. I asked here, what type of series are these? So I'm getting you to think about, is it arithmetic or geometric? So when you look at these numbers, am I adding the same thing every time? In this, if I looked at it as a sequence from this term to this term to this term, I don't think so, right? I'm not adding 5, adding 5, adding 5, adding 5. I also don't believe I'm multiplying by the same thing every time. So that one I would say neither. But this one, just by looking at the formula, is that a linear formula, 3j minus 2, or is that exponential? What format is that? Linear. It's kind of like mx plus b. So since this is linear, if you looked at those numbers, when I plugged in 4, then when I plugged in 5, then when I plugged in 6, you would see an arithmetic pattern there. This one is exponential. And so you would see, because it's exponential, you would see a geometric pattern. You're multiplying, multiplying, multiplying by the same thing every time. Does anybody know what that multiplier would be? 2, the base of the exponent. Every subsequent term would be multiplied by 2, by 2, by 2, by 2. Does anybody know what the common difference would be here? What'd you say? Not 1. The common difference is the same thing as the slope. And the slope is 3. So if you were to plug in 4 and then 5 and then 6 and then 7, you would see the pattern of those answers being add 3, add 3, add 3, add 3. Here you would see the pattern be times 2, times 2, times 2, times 2. And this one is technically linear with a slope of 0, right? Plus 0, plus 0, plus 0, plus 0, because it's a constant. That's a little bit of a special case. Okay. In this next section, we're going to write our own sigma notation. So we're going to try to find the pattern. What would you call what is the pattern here? Times 3, right? So the base of an exponent would be 3. And really, we could do 3 to the, pick a variable, I'll say k. So what does this start at? 3 to the what power? First. 3 to the first power would give me 3. So I'm going to start this thing at k to the 1. And then this is 3 to the second. Does everyone see this? 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, 3 to the fifth. And so where would I end this? 5. Does anybody see the pattern with these? This one's not arithmetic or geometric, but if you just look at those numbers and look for a pattern, what do you notice about all those numbers? They're perfect squares. This is what squared, Bella? 1 squared, this is. 2 squared, this is. Yep, does everyone see that? So when you're writing your sigma notation, the thing that's staying the same all the time is the exponent. The exponent is always 2. It's your base that's changing. Your base starts with a k value of 1 and ends at a k value of 5. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And that would represent that series. Good? What's the pattern in the third one? Like, could you tell me what the next one would be? Yeah. 6/7. So you obviously see the pattern. Now we just have to figure out how to represent it, right? So let's start with the numerator. The numerator is changing, right? Let's let that be our k. And k is starting at 1 and ending where? 5. What is your denominator relative to the numerator? Always one more. So your denominator is just k plus 1. And that'll cover it. So the numerator goes from 1 to 5, and the denominator goes from 1 plus 1, which is 2, to 5 plus 1, which is 6. So taking patterns and writing them. Oh, that's the end of our notes? Look at that. We can get started with this one. We'll probably finish off with this because this is more of a challenging one. Right? You guys don't have a backside to your notes. Okay. So they're giving us a recursive sequence here. A little bit of a challenging recursive sequence because it's using the term before and it's using 2 terms before. So let's just start with this summation notation. It wants us to start with an I of 4 and go up to 7. So we need an A sub 4 plus an A sub 5 plus an A sub 6 plus an A sub 7. That's essentially what we need. we need to use our recursive formula to figure out what is a sub 4, what is a sub 5, and so on. Okay? So with our recursive formula, we already know that a sub 1 is 0 and a sub 2 is 1. We're not going to get to the 4th, 5th, 6th, and 7th term until we find the third. So to get to our third term, we take the previous term, which was what? 1. And we add 2 times the term before that, which is 2 times 0. So that would give you 1. So for our fourth term, we take the term before, which is 1, and add 2 times the term before that, which was, what's 2 terms ago? 1. So that will give us 3. To get to our fifth term, we take the previous term, which is 3, and we add 2 times the term before that, which was 1. That gives us 5. Our sixth term, we take the previous term, which was 5, and add 2 times the term before that, which was 3. 5 plus 6 is 11, and I'm actually almost there. So for the seventh term, I take the previous term of 11, and I add 2 times the term before that, which was 5, which puts you at 21. Then take those 4 values, plug them into the summation notation structure that I just had, and just add 4, 5, 6, and 7. 4th term, 5th term, 6th term, 7th term. Homework is coming around. There you go, dear. Yeah, sure, no problem.
Oh, you know.